So let's start solving some exercises. The first one, we consider this difference equation. So this is a second order linear difference equation, and the exercise is to show that the solution is given by this, where A1 and A2 must satisfy the system of equations. Okay, let's do it. So we have, so here it's exercise 1. So xn plus 2, 2xn plus 2, blah. No, yeah. So xn plus 2 minus 3 xn plus 1 plus 2 xn equals 0, and we have the initial conditions. So because it's a second order, we have to put 2 initial conditions. So x0 it's equal 10 and x1 equal 20. So we are looking for solutions like this. Xn equal lambda to n times some constant c, and substituting on the difference equation, we get that lambda n plus 2 times c minus 3 lambda n plus 1 times c plus 2 lambda to n equals 0. Putting lambda to n on evidence, I missed some c here. C equals 0. We get lambda to n times c. It will be lambda square minus 3 lambda plus 2 equals 0. So we got our characteristic polynomial, and the roots of this polynomial will be the eigenvalues. So let's see. So lambda square minus 3 lambda plus 2 equals 0. And using Bhaskara formula, we know that lambda 1, 2, it will be equal minus b square of 9 minus 4 times a times c divided by 2. So it will be 3 plus or minus 1 divided by 2. So we get that lambda 1 it's equal 2, and lambda 2 it's equal 1. Okay, so the solution will be xn equal some constant a1 times 2 to n plus some constant a2 times 1 to n, which is just this xn equal to n a1 plus a2. So yeah, we accomplished the first part of the exercise. So okay, in the exercise I just called in a different way, just exchange a1 by a2, so a1, a2. So we already did the first part, and now it says where a1 and a2 must satisfy the system of equations. Here we are going to use the initial conditions, okay? So yeah, so exercise 1, and we got that xn it's equal a1 times 2 plus, actually it's the opposite, yeah, confusing. So and so it will be a2 times 2 to the power of n plus a1, and we know that x0 equal 10. It implies that x0 equal a2 plus a1, because 2 to 0 it's equal 1, and this should be equal 10, and x1 equal 20. It implies that x1 equal a2 times 2 to the power of 1 plus a1 equal 20. So this is the system, a2 plus a1 equal 10, and 2 times a2 plus a1 equal 20. And solving, this is a linear system, and then solve for a1 and a2. Then I will let this as exercise. So there's two questions here. What are the values of a1 and a2? I will let it for you to find it out. And the other question is, what's the behavior of the solution? So we see that we have one eigenvalue equal 1 and another equal 2. So this eigenvalue here will make the solution increase as soon as n increase. So the behavior of solution, you can plot it. So it will start with 10 here, x0, and then it comes to 20 here, and it will increase, okay? So it will be some increasing behavior. just by looking at the eigenvalues we can see that. Okay, let's go for the next exercise. So the exercise 2, write the equation, the solution for the difference equation, So here it's the same approach as the exercise 1, but here it's just some general solution because we don't have x0 or x1, so it's just for you to write the solution like this. So some constant 1 times lambda 1 to n plus c2 times some lambda 2 to n, in case lambda 1 and lambda 2 are different, and in case that they are equal. And then you need to write it like this, times n lambda 1 to n times some n, in order to have some linearly independent solution. Okay, I will let this as homework. And let's go for the exercise 3. Solve the following system of difference equation. So exercise 3, the system is xn plus 1, yn plus 1 equal minus 3 xn minus 2 yn 2xn plus yn. Yeah. So here again, it's a linear system, and for finding its solution, which will be xn, yn, it will be equal some constant 1 times the first eigenvalue to the power of n times the first eigenvector plus some constant 2 times lambda 2 to the power of n times the second eigenvalue. So we have our matrix here, let's call M, and then we need to find its eigenvalues. So we need to calculate the matrix M, it's equal minus 3, minus 2, 2, 1. And we need to calculate the characteristic polynomial, which will be determinant of minus lambda I. And we need to calculate the roots of this polynomial, so it will be minus 2, 2, 1, and this is equals 0, okay? Oh, okay, 1 minus lambda. So let's go for it. So minus 3 minus lambda times 1 minus lambda minus 4 equals 0. And then here you are going to get second degree polynomial, and then you will find lambda 1 and lambda 2, and for by setting lambda 1 that you found here, you get v1, and then you also get v2, okay? I'm also letting this for you to do it yourself. And if you have any question, just let me know. Now, exercise 4. So we consider the Fibonacci sequence, which is so we have a term U0 and U1, which is 1 and 1, and we can write the Fibonacci sequence like the UN is the sum of the two previous terms. So the exercise is to find the solution of this second order equation. So here again is similar to the first exercise and the second. So you are going to suppose that UN it's equal some constants times lambda to the power of n, and substituting in the difference equation, you will get the characteristic polynomial, and then you get lambda 1, lambda 2, and by using the initial conditions, you are going to determine the constants 1 and 2, that is here, and then you are done. You found a solution for the Fibonacci difference equation. I also like this as homework. And the exercise 5 is to find the solution for the system. Here again, it's a linear system, and it's similar to the exercise 3. So you're also going to find the eigenvalues of the matrix M, in which M is given by 0, F, 0, R, 1 minus M times F. From here, we already see that one of the eigenvalues will be 0 and the other will be R 1 minus M times F. And then you just substitute the values that is given here. Yeah, so because one of the eigenvalues is 0 and you are searching for no, it's alright, because 0 to the power of n is zero, yeah. So here, for having a linearly independent solution, you need to put that n in front, so you need to do something like this, okay? Times lambda 1 to n. So your solution will be something like this. Okay, I also like this as homework. And now it comes some nonlinear difference equation. So the first question is, does this equation have an unsteady state? So 6, so in the steady state this happens, so it's k n and here it's b. No, it's wrong, it's b plus x bar. So it will be plus x bar it's equal k times x bar, and so it will be b x bar plus x bar square is equal k x bar, and then you get x bar square plus b minus k I x bar, it's equal 0, or x bar times x bar plus b minus k, it's equal 0. So we can see that 0 is one steady state, so, and the other steady state will be k minus b. So yeah, this equation has two steady states. But observe that this steady state just have some biological meaning, because this models some population growth. It just have some meaning if k minus b. So here it's some biological meaning. If k minus b is bigger than 0, or if k is bigger than b. Okay, this is important here to pay attention. Okay, and the letter B asks if these steady states are stable. So it asks you to analyze the stability. So for that you need to calculate the f line of x. Okay, you calculate it. So our f of x is given by k times x divided by b plus x. And then after calculating this derivative, you are going to analyze the stability for each steady state. So first you take x bar equals 0, and then it will be stable if this happens. And then after doing this, you do it also for the other. So you could just say this is steady state 1 and steady state 2. Okay, and then you analyze also if this happened. Okay, exercise 7. In population dynamics, a frequently encountered model for fish population is based on an empirical equation called Ricker equation. So letter A, show that this equation has an steady state given by this. So for doing that, you just do this that approach. So at the steady state, n bar equal f of n bar, and see if you get this value, and show that the steady state is stable provided that this happens. So then you calculate here f line of n, and then you see if f line of n at the steady state is smaller than 1. Okay. And now here, exercise 8, we have a nonlinear system that models some host parasitoid system. So it's nonlinear because we see that our Hn it's multiplying our Pn here. So you're going to have something Hn times Pn, which is nonlinear. So what you need to do here? So the question is, determine the steady state and their stability for this system. And you should assume that F, A, K are positive parameters. So what you're doing to find the first, you find the steady state. You just say that your H bar it's equal your function here, H bar, P bar, and also this other function. Okay. Then you get solving this system, you get H bar and P bar, which are the steady states, and then you analyze the stability. You need to calculate the Jacobian matrix, which will be del F del H and del G del P, and let me see if that's the no, it's incorrect, the Jacobian here. So del F del P and then del G del H del G del P, and then you evaluate it on each of the steady state. Just by looking at this system here, you can see that this 0 is one of the steady states, okay? And then you are going to also get some non-zero steady state, and you have to analyze this for each steady state, and then once you get your Jacobian matrix evaluated at the steady state, you are going to calculate the eigenvalues of this Jacobian matrix, and it will be stable if the eigenvalues satisfies this, okay, if they are smaller than 1. Okay, and as I said, this is the paper for the Verhulst equation or logistic equation, and this is the book that I got the exercise from. Okay, so I just give some tips to how to solve this exercise. I hope they are enough, and I'm going to record now another video giving some some guidance on the exercise, the activity 2 that should be handled on the next week. So yeah, I'm going to try to explain the system and the model and try to help you with this activity.